Good morning. Okay, so um, this week we're going to learn about composite material, right? I'm going to give you a few examples about composite materials, and I'm not going to go into too much detail on the materials used in the industry. I'll give you a few examples. But next week you'll learn about biocompatible materials, and you will learn more about that sort of thing. Okay, so um, so this week we're going to learn about composite material. Okay, composite materials. Composite materials are actually materials. They are all around us as well. So, what are they, and how long have you been around? How long have they been around, and any composite around you? Okay. So, how much do you know about composite materials? What are they? Okay. We're going to answer these questions right, today. And how long have they been around? So anyone know about anyone know anything about composite material? Composite material are materials that usually we think of as new material, right? That combine different materials together to get better performance. But in fact, composite material have been around for a long time. It's not just the new material that we've seen, right? But it has been around for a long time. And in fact, if you've come to class today, you've used a few composite material without you even knowing. And we will look at examples of those composite materials. Okay. Okay. There's a YouTube videos on composite material that you can go and have a look at. It's kind of QR code there, or follow that link there to have a look at what is composite material. But like I've just mentioned just now, that composite materials have been around for a long time, right? So, in fact, during the times of the Egyptian pharaoh who built the pyramid, composite material has also already been used. Okay, so they used composite material to build the huts for the workers. Um, the workers who built the pyramid. Okay, so basically, you might think of this as a simple brick, right? But it's not that simple. So it's not just made of clay. Usually they put in some straws, in some husk like rice husk or wheat chaff in that to increase the strength of the bricks. In fact, nowadays we still do that. We still put some rice husks in clay brick to increase the strength. Right? So it's been around for thousands of years. Right? The concept of composite materials has been around for thousands of years. So basically, we put two materials together to improve the properties and enhance the performance um, of the material. Okay. Okay, so when we think of composite material nowadays, we think of like high-tech equipments, like in airplanes or sports equipments, right? So like this tennis racket. Okay, so usually tennis racket would have been made. Well, originally it was made from wood, right? But it was like quite heavy and clunky. So in the around the 60s, they started to make uh, tennis racket from aluminum, right? Aluminum alloys, aluminum. So it's lighter, and you can have like a bigger sweet spot in the racket. So you started to see the change in the trend of the type of playing. Right? So before the 70s, you see a lot of servant bodies, and because the racket is quite heavy, so you can't really serve really fast. So you serve and you go up to the net and like, you try to block. In the 70s and then the 80s, you start to get bigger serves because the racket is lighter. You can swing it faster, so you get like bigger serves. Right? And in the around 90s, around 2000, you start to get composite tennis racket, right? That's made from carbon fiber. That is extremely light and really, really strong. So now you start to get really, really big serves. Like until nowadays, like this, the serves, the speed of the serve like could be up to about 200 kilometers per hour. Right? So it is really, really fast. And that fast serve can be achieved by a better equipment made from composite material. Okay? Imagine using a wooden racket and trying to serve those like big serve. You might be able to do it for the first few serves, and then you get tired really, really easy, right? So basically, the composite material that we use, like in sports equipment, like tennis racket, uh, golf clubs, etc. We try to enhance the performance of that equipment by making it lighter, but at the same time stronger as well. Okay, the same with airplane, right? In the around the First World War, when airplanes were started to be used in the war, the planes were actually made from wood and canvas. Okay, and then uh, and then we started to have more advanced material. In the Second World War, the planes started to be made from like steels and aluminum, okay? And that kept going, and you will see, well, you would see a change not only from the actual appearance of the plane from around the Second World War to, of the First World War to the Second World War to now, but also the type of engines that the planes were using. Right, so up to about the Second World War, you would probably associate the planes with a propeller engine. Okay? But because of the advancement in the material, we started to get jet engine around that time. And nowadays, propeller plane is still around, but um, we usually we use the jet engine, right? And jet engine can be uh, can be made possible by the advancement in material and also composite material in particular. And also, if you look at like modern airliners, the modern airliners use a lot of composite material. For example, the uh, Boeing Dreamliner, Boeing Dreamliner 787 use about 50% by weight composite material compared to other type of planes. Right? Okay, so composite materials are around us, right? We have like sports equipment, we have uh, wind turbine that's made from composite material because we want the turbines to be really light but strong at the same time. So if we use like metals or if you use metals, it will be too heavy, and if you use plastic or polymers, it will be too weak to withstand the wind load. Right? So we use composite material to make it turbine. Like bulletproof jackets or helmets. Right? These are bulletproof because we have composite material of Kevlar fiber, and that Kevlar fiber can absorb a lot of energy. If you remember the lecture about the impact energy, right? Most material, when they absorb energy, will deform a lot, and then if that material is a ductile material, right? it will deform a lot, and it will absorb a lot, and it will absorb a lot of energy. For ductile material, they don't absorb a lot of energy, right? But they will break into different pieces. We can have a piece of steel as the armor in the bulletproof vest, but it will be really heavy. And steel is really strong and it can absorb a lot of energy, right? But at the same time, it's really heavy, and we don't want to walk around with steel plates, right? Carrying steel plates around all day. So they improved that by using Kevlar fiber, and Kevlar fiber can stop bullet because Kevlar fiber can absorb a lot of energy before breaking. Right? When it breaks, it absorbs even more energy. So it will absorb a lot of the kinetic energy of the projectile, of the bullets. Okay, so that makes it really useful. But at the same time, the Kevlar fiber are really light compared to steel. Right? So that's why we use like Kevlar fiber bulletproof vest instead of like carrying around like steel plates. We have glass fibers furniture, which is also composite material. So you might have heard of like glass fiber or fiberglass furniture and stuff like that before. So those are actually composite material, like fiberglass hull of a ship or boats, or even concrete. Right? So if you come to class today, you have already used composite material today, right? So the concrete is a composite material, right? So and if you come by car, even the tire of the car is a composite material. Okay, so what is composite material? Okay, so a composite material is a material that is made by combining two or more materials. And usually those two materials have different properties. And when you combine them together, you make a material with unique properties that combine the properties of those two starting materials. Okay? The two materials work together to give the composite unique properties. And within the composite material, you can tell the different materials apart. They do not dissolve or blend into each other. So you have a clear phase boundary. Okay? So for example, alloys, say a brass alloys. An alloy is when you mix two different elements together, like brass, you're mixing zinc with copper, you get brass. So you have zinc, you have copper, two different materials, but when you mix them together, they are not composite material, they are alloys, because those two materials like blend together to form a new material, right? And you cannot see a clear phase boundary between zinc or copper. Okay, even though brass has better properties than zinc or copper, right? Which like satisfy this criteria here, but they do not separate in such a way that you can identify this part is zinc, this part is copper, right? Those are because of that, alloys are not composite, right? Alloy is just another different class of material altogether. Okay, but for example, concrete, you can see that you are mixing aggregate, rocks and sand with cement, right? And you can clearly see the aggregates, the rocks, the sand, and also the cement. You can differentiate between different materials. You can they have clear phase boundaries. Okay, so that is what a composite material is. Okay, so next we will look at the different categories of composite material by considering the constituent materials. Okay, so when we classify composite material, we can use two different criteria. The first criteria is to look at the matrix. The second criteria is to look at the reinforcement phase. Okay, so basically, composite material consists of the matrix and the reinforcement. Right. So usually the matrix is the starting material. Not always the case, but that about 80–90% of the case, the matrix is the starting material, and then we put in the reinforcement phase to enhance the property of the matrix. Okay, so the matrix phase is the continuous phase. The purpose of the matrix phase is to transfer stress or transfer the load to other phases and protect other phases from the environment. And we can have three different types of composite if we use the metric phase as the criteria. We can have metal metric composite, ceramic metric composite, and polymer metric composite. Okay, so the criteria to classify composite material is depends on the type of matrix that we use, right? Whether it is a metal metric composite, ceramic metric composite, or polymer metric composite. So for metal metric composite, basically it means that we have the metal as the main phase, and then we add in some other stuff, some other reinforcement to make that metal stronger or harder or tougher. Right? A ceramic metric composite is when we have the metric phase, it's made from ceramics, and then we add in some other stuff to make it tougher, stronger. A polymer matrix composite is a composite material that we have a polymer as the matrix, right? And we add in some other reinforcement like fibers. Like for example, glass fibers is a polymer matrix composite because we have the resin, which is the matrix, which is a polymer, and we add in some glass fibers as the reinforcement. Okay, so if we take the matrix as the criteria, we can have metal metric composites, ceramic metric composite, polymer metric composite, right? So next, if we consider reinforcement phase as the criteria for our composite, we can classify composite material as the continuous fiber or short fiber, and then particulate. Right? So we will look into that in more detail. But in this slide, I just want to clarify what is a matrix and what is a reinforcement. Right? So a reinforcement phase is the phase that you usually put in to improve the property of the matrix. Right? So the reinforcement phase is the discontinuous phase or dispersed phase. Right? So that means it's just like distributed evenly within our composite, right? Compared to the matrix phase, which is the continuous phase. That means it's all connected, and within that continuously connected space, we have the reinforcement dispersed in that. Okay? And the purpose of the reinforcement is to enhance the matrix properties. Okay? And the reinforcement can have different geometries like fibers, particulates of particles, or like flakes and stuff. Okay, so next we will look at the design goal of composite material. So if you look at this material selection chart, on the x-axis we have density, on the y-axis we have Young's modulus or stiffness, right? So the okay, so in any application, usually we want like really high mechanical properties such as Young's modulus or strength, like high value on the y-axis, right? But at the same time, we want it to be quite light. So we want the density to be quite low. Right? So what we want it on this side. So we want it to be on this side of the graph of the x-axis, for the y-axis, we usually want it like higher up in the y-axis to be stiffer, to be tougher. Okay? So if it's flexible, it's gonna be really bendy. It's gonna like get bent really easily. But if it's too stiff, it can break quite easily as well. So we want it to be like somewhere around this range. Okay, we want the Young's modulus or the elastic modulus to be around somewhere around this range. But at the same time, we want the density to be quite low. Okay, so you can see that for metals, we have really good Young's modulus, so it is in this range, but the density is quite high. Right? Other material with low density, such as foam, rubber, wood, and polymer, right, have relatively quite low density. So 1,000 kilogram per cubic meter, that's around the density of water. So basically, a higher number than 1,000, right? That means it will not float in water. Lighter than 1,000 kilogram per cubic meter, and these material will float in water, right? So that's roughly the ballpark. So we want it to be like lighter, but at the same time really stiff, really strong. So what do? We create a new type of material, which is composite material. Okay? As you can see, it is just a little bit like denser than water, but at the same time, it's got the same mechanical properties as metal. Okay? And you can see that the density can be about like 1/10 of that of metal, so that a lot lower than a density of right? We get the same mechanical properties, like in the same range as metal, but at the same time, density is about like 1/10. Okay, so this is like our design goal. Right? So in fact, for like the really best material, the real goal would be somewhere around here. Right? So when you get like high enough Young's modulus, but really light, that's like almost impossible. But we are getting there. We're getting there. Okay, because we are improving the composite material all the time. So we are moving the density along this axis here, like go to the left to go lighter. But at the same time, we are making it stiffer and stronger, so we go going up that way. So it will come like somewhere around there. Okay, so okay, so in fact, the goal of composite material is to achieve a combination of properties that is not displayed by any single material, and also to incorporate the best characteristics of each of the component material. Right? So, for example, in the composite material, for example, we have say fiberglass. Right? Glass is a type of ceramics, so you have like relatively quite high stiffness, but also it is quite dense. Fiberglass, we are mixing glass fiber with resin, which is polymer. So you can see that polymer has lower mechanical properties than glass, but it is also lighter. It is less dense than glass, right? So when you mix polymer, which is the resin, and glass fiber, you can make composite material, right? So you can get the lighter property of polymer, whereas you can get the mechanical property of ceramic. Right? So you combine two materials and you take the best characteristics of those two materials and combine it to get a new type of material. Okay, so next we'll look at the classification of composite material. I've just touched audit briefly before, right? So we can use two criteria to categorize or classify composite material. We can either use the matrix as our criteria, or we can use the reinforcement as our criteria. Okay? If we use the matrix as our main criteria for classification, we can categorize composite material into metal matrix composite or MMC, ceramic matrix composite or CMC, or polymer matrix composite or PMC. Okay? So for metal matrix composite, the matrix is made of metal. For ceramic matrix composite, the matrix is made of ceramic. For polymer matrix composite, the matrix is made from polymer. Right? So if you're using the matrix as our criteria, but if we are using the reinforcement phase as our criteria, we can categorize composite material as particle reinforced composites, fiber reinforced composite, and structural composite. Right? So particle reinforced composite is any of these types of composite material, whether it's MMC, CMC, or PMC, where you put in particles in there to improve the property. Okay? And for fiber reinforced composite is when we are putting fibers inside any of these composite material to improve the properties. And the structural reinforced composite is a little bit more like complex. We'll look at the example of the structural composite as well, but it's not like just a particle or fiber. You have actual sheets or actual structure that can increase the properties. Like for example, honeycomb structure in like cardboard box, or like ridge folding pattern in between two sheets of paper that makes the cardboard box stronger, right? So that is a type of structural composite. Okay. Okay. So remember that reinforcement is added to the matrix to improve the property of the matrix, right? So for MMC or metal matrix composite, we have to consider what are the main advantages of metals, what are the main characteristics and properties. Metals are quite strong, metals are quite tough, metals are quite stiff and quite hard, right? But at the same time, metals are quite heavy, and when you use metal at high temperature, you can get some creep, right? If you go back to the lecture before the midterm about mechanical property. Okay, at high temperature, the strength of metal decreases, and you can get some creeps or some deterioration of performance. Okay, so those are the limitations of metals, right? So we can put in some reinforcement to increase the yield strength, to make it stronger, to increase the tensile strength, to improve creep resistance at higher temperature. Okay, we do that by usually adding some ceramic powder, ceramic particles, or sometimes we are using ceramic fiber. Okay, and when sigma y or yield strength increases, you will have an increase in hardness as well. Okay, sigma y is yield strength. Yield strength is the stress that you require to permanently deform a piece of material. Right? Tensile strength, TS, is the maximum strength that a material can withstand. Okay, so sigma y is yield strength, the strength that you need to permanently deform it. Okay? So basically, it is the elastic limit of the material. Okay. Okay, so tensile strength. Tensile strength is the maximum strength that that material can withstand before failing. Okay, so we put in the reinforcement to increase all these properties of metals, right? So metals are relatively quite strong, but we can make it stronger. We can make it harder by adding some reinforcement. Next, we'll look at the CMC or ceramic matrix composite. Okay, ceramics are quite strong. Ceramics are quite hard, right? So it's got high hardness, it's got high strength, but ceramics are notoriously brittle, right? So it breaks really easily. Ceramic breaks really easily. So we usually put in some other reinforcement to increase the fracture toughness of KSC. Okay, KSC is fracture toughness of material. Right? So I think I've talked about that a little bit in the class before the midterm as well. So ceramics, because ceramics are brittle, we want to make ceramics tougher. So we add in some metal fibers or sometimes metal particles or polymer fibers, right, to increase the fracture toughness, so to make it less brittle. Okay. Okay. For example, concrete. Concrete is really strong, really hard, right? But concrete is strong in compression only, right? So when you squeeze it, concrete is very strong. But when you are pulling it, concrete is quite brittle, right? It's not very strong at all. So we add in the reinforcing steel bars inside concrete to make it stronger in the tensile loading when we are trying to pull it, right? Okay, so okay, so in a concrete beam, right, or a bar or beam, you will see that there's more reinforcing steel near the bottom of the beam than at the top. Okay, because when you have a beam or a bar, the loading in that beam or that bar is bending, right? So when you have a beam or a bar, you have like some sort of bending load. So at the bottom, we'll experience tensile loading, right? So when you have like you start off with a straight beam and then you start to get like bending beam, right? At the bottom, you try to get longer. That means you will get tensile loading. At the top of the beam, you will have compression or compressive loading. And concrete is really good under compression or compressive loading. So at the top, we do not have to reinforce too much. But at the bottom, when you have a lot of bending, you have a lot of tensile stress. That's why you put in a lot more reinforcing steel near the bottom of the beam, okay, to help with the tensile loading. Because steel is very good under tensile, whereas concrete is not very good under tensile at all. So we put in steel reinforcement to increase the fracture toughness of the concrete. Okay? So the steel will absorb the tensile loading so that the concrete doesn't have to absorb that tensile loading, and it will withstand the loading much better. It will not crack easily. Okay, so next, PMC. PMC or polymer matrix composite. Okay? Polymers are very light, right? So that's the main advantage of polymers. They are relatively quite cheap, right? So they are light, they are cheap, but the strength of polymers are not very high. Okay, so we have to do something to improve the strength or other mechanical properties of polymers. So, for example, we add in glass fibers, or we add in Kevlar fibers or carbon fibers to improve the strength of the polymer matrix. Right, so we can increase Young's modulus, we can increase yield strength, tensile strength, we can increase creep resistance of polymers. Okay, okay. We can do that by putting in reinforcement, whether it is fiber or particles. Hmm? E is Young's modulus or elastic modulus. So basically, polymers have really poor mechanical properties compared to other groups like ceramics and metals, right? You can see here, polymers have like really poor Young's modulus compared to ceramics and metals. But polymers are lighter, so we want to make a material that is light because we want to use polymer. But at the same time, we want to make it stronger, tougher by increasing Young modulus, yield strength, tensile strength, by adding in some other reinforcement. Okay, so let's the classification by the metric is quite straightforward, right? So it depends on the type of the matrix, and you can classify it quite easily. But the classification by using reinforcement can be a little bit more tricky because you can have some like subcategories, right? So you have particle reinforced, fiber reinforced, and structural, right? For particle reinforced, you can have large particle, or you can have like really small particles, which is called dispersion strengthened composite. Okay? So for particle reinforced composite, you can have like large particle reinforced or really small particles reinforced. For example, in this case, is for large particle reinforced is concrete, or dispersion strengthened is cast iron. So looking in more detail there. Okay? For fibers reinforced, you can either have continuous or long fiber. Right? When you have continuous fiber, you can have like alignment of the fiber. So the properties will be some sort of anisotropic. For discontinuous or short fiber, so for fiber, you can say that you have two types. You have long fiber, which is continuous fiber, or you have short fiber, which is discontinuous. Right? Like fiberglass are usually short fiber because you have short short glass fiber mixing in the matrix. Okay? But you can also have like long continuous glass fiber as well, like when you make like pressure vessel using composite material. Okay? And when you have short fiber, the short fiber can sometimes be aligned, so the fibers are all in the same direction. When I say align, I mean the fibers are in the same direction. Right? Or the fibers can be randomly oriented. Like Kevlar fiber in automotive parts. Right? These are long continuous fiber, and for short fiber, like glass, fiberglass furniture. Okay. For structural composite, we can have either laminates or sandwich panel. Right? So if you've been on a plane, the floor of the plane is usually made from structural composite. Okay, so usually they are either laminates or sandwich panel, or sometimes they combine the two. Okay? Because we want the in-plane stiffness, we want it to be safe. So, and when we walk on it, we will think that we are walking on solid floor, right? But in fact, it is just like a few millimeter thick piece of composite material. We don't want to make it from like concrete because of the weight, right? Like the floor on an athlete. We don't want to make it out of concrete or like thick sheet of metal because of the weight. So we are using structural composite to make it feels like we are walking on a thick sheet of metal, but really we are stepping on like really a few millimeter uh, piece of metal with some stuff inside, right? So those are sandwich panels or laminates. We'll look into more detail. Okay, so um, first we'll look at the particle reinforced composite. Okay, like I mentioned earlier, you can have either large particle composites or dispersion strengthened composite, right? So depending on the size and depending on how those particles uh, can help improve the load improve the mechanical properties of the matrix. Right? Okay, so for large particles composite, the improvement in mechanical properties come from the strong bonding between the matrix and the particle interface. Okay, so say you have a piece or a cube of large particle reinforced composite like concrete. You have matrix, which is made from cement, particles, which is rocks and gravel. So you have this strong bonding so that the load is transferred to the aggregate quite easily. For this type, for large particle composite, the particles can have quite a variety of geometries. But the particle should be approximately the same dimension in all directions, or equiaxis. Okay? In other words, you can have different shapes and sizes of the particles, but ideally, the particles should be about the same size in the x, y, and z axis. Okay? So either spherical or some sort of like cubic, like that's the ideal shape. But it doesn't have to be. It doesn't have to be. And for effective reinforcement, the particles should be small and evenly distributed throughout the matrix. Small in this case, small compared to the whole structure. Right? It doesn't have to be like really, really tiny, but it has to be small compared to the whole structure so that the particle can stack together more efficiently and withstand the load more efficiently. The next type of composite material is dispersion strengthened composite. The particles are normally much smaller with diameters between 0.01 and 0.1 micrometer, or about 10 and 100 nanometers. So for comparison, the thickness of human hair is about 100 micrometer. So this particle is about 1,000 times smaller than the thickness of human hair, like for one particle. Okay? So when the particles are small, they can be dispersed more evenly throughout the material. And when they are this small, they are in the same length scale dimension as dislocation. Right? Dislocation is a defect in the material, right? And material can be formed by moving the dislocation. So when you have this small particles in there, in the same length scale of dislocation, these particles will try to stop the movement of dislocation. So making the movement of dislocation harder, that will make it stronger. Right? The material is stronger because the dislocation is more difficult to move. Okay, example of particle reinforced composite. Okay, the first one is the symmetric carbide, cutting tools, saw tip, etc. So if you look closely at the tip of the cutting tool, It's not like just pure metal. If you look closely under microscope, you can see it is actually a metal matrix composite, with particles. In this case, it is tungsten carbide particles that is glued together by cobalt, which is uh, a metal matrix. Right? Tungsten carbide is really, really hard, but it is also brittle. Okay, so we cannot use tungsten carbide to form like the tip alone because it is very brittle. So when you cut something, the tip will hit on that material and it will break. But when you break the tungsten carbide into small particles, and we use cobalt, which is a metal, to bind them together, to bind all those particles together. Now we have cobalt, which is quite ductile and can absorb all that energy, all that vibration, right? And we have ductility from the cobalt, but we have the hardness from the tungsten carbide. Right? So it improves the properties of both the cobalt and the tungsten carbide. Right? The cobalt is really soft, it is very ductile, it's not very hard at all. But to cut something, we need a material that is harder to cut other material. Right? Tungsten carbide has the same level of hardness as diamond, right? Just a little bit less than diamond. It is really hard, but it is brittle, so we have to bond it with cobalt to make it more ductile and more tough. Okay? So this type of composite material, like metal matrix composite, that is used in cutting tools, sometimes called cermets. Cermets, C-E-R-M-E-T. Cermet is short for ceramics and metal. Okay? So you have ceramics, which is tungsten carbide, and metal, which is cobalt. Okay, so we have tungsten carbide, or sometimes we have titanium carbide embedded in metal, so that the stress can be distributed to the metals, and that make it tougher. Okay, so next type of composite material is concrete. Okay? Concrete is a composite material. It is a particle reinforced composite, but it is also a ceramic matrix composite. Okay, because we have cement, which is a ceramic, as the matrix, and we have aggregates, which is the which is the rocks and gravels and sand, okay, acting as the reinforcement. Okay, so the matrix is the cement. The cement is strong and quite expensive. Right? So we want to make a material that is strong but a little bit cheaper than cement. Okay, so we add in some natural material like rocks and sand to make it cheaper, but equally as strong. Okay, and those sands and gravels and rocks, those are uh, called aggregates. Like they're all together, they are called aggregates. Those are particles which is strong, durable, and cheap. The next type of particle reinforced composite is the polymer matrix composite. An example would be car tire. Okay, so I think you already know that car tire is made from rubber, right? Rubber is a polymer, but pure rubber is not very hard, not very strong. So we have to enhance the property of the pure rubber. We do that by adding particles of carbon black, right? We add particles of carbon black, which is basically just like small particles of carbon. Okay. So if you look at this microstructure, you can see rubber as the matrix, and all these particles are just carbon particles in the size between 20 to 50 nanometers. So it is actually a dispersion strengthened composite, right? Because the range of the particle size is between 20 to 50 nanometers, and because of these particles, the dislocation will move much more difficult. So the strength increase. Okay. Apart from the increase in strength, you have an increase in hardness as well. Okay. So when you add carbon to car tire, you improve tensile strength, but at the same time, you lose uh, friction and you will lose some like crack feeding property. Okay, let's have a look at some example of ceramic or metal-metric composite with cemented carbide, etc. Right. So, for example, you have tungsten carbide and cobalt. Right. So usually you mix tungsten carbide powder with cobalt powder. Okay. You mix them together and then you sinter it in a method called powder metallurgy. Okay. In powder metallurgy, you mix the powder together and then you sinter or you put it in the furnace at high temperature, but not not as high as the melting temperature. So those two type of powder will mix together and form this structure, and it can be used to coat or to make, say, for example, drill bits, cutting tools like circular saw, like this. Can you guess what this is? These are drills that we use to drill holes uh, for oil and gas, right? So these are big drills, right? So the diameter could be like 30 centimeters up to like a few meters, right? So the cutting edge is actually made from cemented carbide. Okay, the whole thing is not made from cemented carbide, but the cutting edge is made from cemented carbide. Okay. What about this picture here? Can you guess what they are? This picture on the lower right. These are the drills that dentists use to like um, to to drill the teeth, right? Different shaped drills. They are also made. The tips are also made from cemented carbide as well. These are basically dentist drill. Okay. The reason why they use this instead of like pure metal drills because it is much harder, so it is more wear resistant. So you can use it for longer without like breaking. Okay, so let's have a look at why we put in some carbon black inside rubber. Right? So one of the unintended consequence of adding the carbon black in natural rubber to make car tire is that it makes the car tire black, right? Because we add in carbon black. Then the reason we want to add carbon black is because we want to improve the hardness. In other words, durability of the car tire. Okay? But there's different amounts of carbon black that we can add in to the rubber. Right? For example, if we add in a lot of carbon black, you will make the car tire really hard, right? Because we want to improve the hardness. But when the tire are really hard, you would get like when the tire are really hard, you will have better. It will last longer, but you will get worse grip. Right? When you have hard tire by adding a lot of carbon black. But if you add in just a little bit of carbon black, the tire is softer. You have softer tire, and because of the softer tire, you have better grip. But also because of the lower hardness, they're not very durable, right? So hard tires are great for long distance everyday use, whereas soft tire for speed, right? So for example, in sports car or in racing car, usually they will put on softer compound tire. Okay, they put on softer compound tire because they want better grip. They want to go faster. Okay, uh, why softer tire has better grip? Because of the softer uh, property of the rubber, it can go between the crack on the road much easier. So in fact, you have better contact with the road. So you get better grip. And because of the better grip, you can go faster because you can transfer the rotational speed of the wheel to the road much better. Right? But because of that, because of the higher contact to the road surface and because of the softer tire, it wears much quicker compared to harder tire. Harder tires don't grip the road quite so well, but because they are harder, they will last longer. Right? So you have to balance between those two factors. Okay, so next example is concrete. So what is concrete? Concrete is a particular type of composite material which is a ceramic matrix composite, right? But at the same time, the reinforcements are also ceramics. So it is a particular type of some special type of ceramics when the matrix and the reinforcement are the same type of material. Usually, we use different material from different groups to improve the property of the matrix. Right? For example, fiberglass. Right? We use glass fiber, which is a ceramic, to improve the property of the resin, which is polymer. Right? Or reinforcing steel in concrete, for example. But concrete itself is also a composite material where the matrix is ceramic and reinforcement is also a ceramic. Okay. Concrete consists of cement, or the full name is called Portland cement, plus sand and aggregates, like rocks, crushed rocks, etc. Concrete are very strong, very hard, but brittle. Like I mentioned earlier, that's why we have to add in some reinforcing steel to improve the tensile property of the ceramics. concretes are quite heavy and cannot be recycled. Okay, the density of concrete is about 3,000 kilogram per cubic meter. Right? So roughly the same in the same range as the density of rocks. Okay, so concrete is made from cement plus sand plus aggregate. So first we have to know about what is cement. Okay, so Portland cement is the most widely used type of cement in construction or in engineering application. There are other types of cements. They are not as popularly used as Portland cement because they are usually more expensive. Okay? Portland cement itself is relatively quite cheap, but uh, but compared to natural materials like rocks, aggregates, cement can be quite expensive, right? But compared to other type of cement, Portland cement is relatively quite cheap. The reason for that is the raw ingredient for making Portland cement are natural ingredients like limestone, clay, and iron ore. Right? We take all these natural materials, we crush them all together, and then we burn them in a rotating kiln or furnace. A rotating furnace called a kiln. Okay? We get this rock shape about like thumb size called clinker. So clinker is the product from crushing and burning all these materials together. But clinker is too big, it's about thumb size, right? So the surface area is quite small. We want to make the surface area bigger, so we want to make the clinker smaller. By crushing the clinker into small powder, we increase the surface area of the cement. And we add in gypsum or calcium sulfate to retard the reaction, to make the reaction a bit slower. So we get Portland cement. Okay? So by mixing these three natural ingredients and burn them, like we crush them and then we burn them in the kiln, right? We get clinker. And if we look closely at the clinker after crushing the clinker and turning the clinker into powder, right? If we look closely, all these three materials turn into three different types of chemical compounds, right? They are reacting to each other under high heat. That will give you tricalcium aluminate, tricalcium silicate, and dicalcium silicate. Okay? Right. So in clinker, there are three main active ingredients. Let's say tricalcium aluminate, tricalcium silicate, and dicalcium silicate. Or we can call it A light, B light, and C light. A light is tricalcium silicate, B light is dicalcium silicate, and C light is tricalcium aluminate. Okay? Okay. And if you look at this graph here, you can see that the x-axis is the time, the y-axis is the strength. So basically, what happens when you mix the cement powder with water, and you get an increase in strength after the hydration reaction. And you can see that initially the C light and the A light, right? The C light and the A light, tricalcium aluminates and tricalcium silicate, react much faster, and you get an early increase in strength from these two chemicals, right? So the A light and C light, you have rapid setting, and so you get early strength from these two chemicals. But as you can notice on this graph here, the strength is not very high for these two chemicals, right? So you have rapid setting but low strength. On the other hand, dicalcium silicate or B lights have slower reaction with water. You can see that the slope is slower initially, right? So the strength increase very, very slowly, but it takes a long time to increase, and then it gets up to a very high strength, right? So B light, you have slow reaction during hydration, right? But you have higher strength. So the time it takes to reach the maximum strength of B light is about 1 month, about 28 days. For A light and C light, it's about 24 hours to get the maximum strength. Right? So you get the early strength from A light and C light. You get the ultimate strength or the final strength from B light. Okay. So next we'll look at different type of cements. Okay. The most popularly used cement is called Portland cement type 1 or general purpose. Okay? You can use it to cast into structure. You can use it to mix into mortar to like grouting your wall surface, etc. Type 2 is the low rate of heat generation and moderate resistant to sulfate. Right? So all these type of cements are different by changing the amount of all these three phases, right? A light, B light, C light. Okay? So for type 3, we have a rapid setting. For some construction, when we want the strength to come early, we want to finish early, and we don't care so much about the final strength, we use type 3. Right? For example, when you are building something in water, in the river or in the sea, we want it to set really quickly, so we choose type 3. And in type 3, we have a lot more A light and C light than in type 1. Right? So, because we want early strength, we want it to set really early. Okay. Type 4, we have a low rate of heat generation. That means we want reaction to be quite slow, so we have a lot more B light than A light and C light. And type 5 is the sulfate resistance and marine application cement. Okay, so concrete consists of Portland cement, sand, and aggregate, right? So we've looked at Portland cement. Next, we'll look at sand. Right? The next ingredient of concrete is sand. So sand is chemically silica, which is silicon dioxide. Right? So sand is silicon dioxide, right? And it is a fine minerals. The size of the grain of sand that we use in concrete is between 0.1 to 1 millimeter diameter. Right? So 0.1 millimeter is about 100 micron. Right? So between 100 micrometer to 100 micrometer to 1 millimeter. Right? So basically the smallest size of sand that we use has the same dimension as the human hand, right? The thickness of human hand. All sands contain some absorbed water because sand particles have a lot of surface area, and absorb moisture from the air, right? So you have absorbed water, and sand is used to fill voids between the coarser aggregates. Okay, so when you pack rock together, you have holes between those pieces of rock, right? And sand can go in and fill in those spaces to make the structure denser and to use less to use less cement as well. Okay, when we use sand to fill in the void between the coarser aggregate, we get higher packing factor. That means lower space, reducing the amount of open space or interconnected porosities inside the finished concretes, and reducing the disintegration of concrete due to repeated freezing and thawing during service. Okay, so next ingredient of concrete is aggregates or rocks. Okay, rocks or gravels. Right? So rock and gravels, aggregates must be clean, strong, and durable. So you can or you cannot just use any rocks or gravels. Those rocks or gravels must be strong and durable and clean. Right? Before using it, you have to clean it. You have to soak it in water for a few times, shake it to get rid of all the powders that stick to it. And angular aggregates are preferred. Angular aggregate particles are preferred because the angular aggregate provide better strength due to mechanical interlocking between the particles. Right. So, for example, these are rocks that we use in concrete, right? And if you have angular aggregates, like in this picture here, the strength could be higher than the aggregate in this picture here, right? When you have rounded aggregates, when you apply the load, the aggregate will just like slide past each other, right? They're not catching, they're not interlocking, right? So you get lower strength for more rounded aggregates. But when you have angular aggregates, like in this picture here, the particles are sort of like interlocking with each other. You get better load transfer, you get higher strength. The aggregate particle should not be larger than about 20% of the thickness of the structure, or it will cause the holding effect. Right? So the holding effect is when you have the stress concentration at that point, right? Because you have big particles, and then you have like small particles around it. Okay, so that's not ideal. So usually when we design a structure, say a beam or a floor, we have to know how thick the beam or the floor is, and we choose the aggregate size to be less than 20% of the thickness. Okay, so in concrete we have cement, we have sand, we have aggregates. The only ingredient that's left is water, right? So we mix water with cement, and we will get a hydration reaction. Okay, hydration, uh, hydra. That's the Greek root for water, right? The Latin root for water is aqua, right? So hydration reaction is basically the reaction with water. In this case, cement hydration is the reaction of cement with water. And you can see that for tricalcium aluminates, react with water, you get this structure here, you get another type of chemical plus heat. Dicalcium silicate react with water, you get calcium silicate hydrates with heat. For tricalcium silicate with water, you get calcium silicate, hydrated calcium silicate, and also calcium hydroxide. Okay, so these are hydration reactions, and they are exothermic reactions, right? So as you can see, all these three chemicals give out heat when you mix them with water. That's one of the reasons why concrete is hot when you initially mix it, right? And what happens to materials usually when they are hot? They sort of like expand, right? And when they cool down, they shrink. Okay, so so when concrete is expanding, when it is mixing, because of the hydration reaction, is expanding, and it is still quite soft, so it can expand. But when it is already set and it is cooling down and it shrink, you start to get internal stress, right? By drying shrinkage, and you start to get cracks within your concrete if you don't control the heat dissipation, right? So if you're casting big structure, sometimes you have to cool it down. Okay. For example, you can find this in documentary on YouTube. Like when they're casting the foundation of Burj Khalifa or the Petronas Tower, they have to put in some ice, liquid nitrogen, in the concrete to cool it down, right? Because the thickness of the foundation is so huge, you have a lot of buildup of heat from the hydration reaction. So they have to put in some ice, some liquid nitrogen, and some dry ice as well, I think, to cool it down, to cool down the concrete. They don't want the concrete to expand too much while they are pouring it, while the concrete is hot, because when it cools down, it will shrink, and that will cause crack. Okay. Okay. Next, we look at the curing and properties of concrete. Right. So, like previously mentioned, right? In cement, you have three main active ingredients: A light, B light, and C light. Right? And they react to water differently. They react to water differently, right? So A light and C light react faster with water, and B light react with water more slowly. And the strength of the cement and the strength of concrete, depending on the reaction of A light, C light, and B light, right? So, and you can see that the high strength come from the reaction of B lights and water, right, to get your higher strength. But it takes a long time. So that means for concrete to achieve the high strength of the concrete that we require, it will take a long time as well. So, hence the curing process. So basically, concrete is expected to be cured for 28 days until it reaches the optimum strength. But because this curing process depends on the hydration reaction, so what it means is if we leave the concrete alone, you will get evaporation of water that we mix in the concrete in the first place, right? We have to leave it alone for 28 days until it develops strength. But if we leave it alone, especially in hot countries like Thailand, you will have a lot of evaporation of water from concrete. So you will not have enough water for the hydration reaction. So you will not have enough water to produce concrete with high strength. So we have to cure it. By curing, I mean we have to uh, keep the water inside the concrete. We don't want the water inside the concrete to evaporate out. Okay, we do that by wrapping it with like burlap, burlap sack cloth, soak in water, and just cover the structure for like a few weeks. Or we can use like ceramic wrap, cling wrap to wrap the concrete as well, right, to prevent evaporation from the concrete. So that's the curing process. We need to do that for at least 28 days for concrete to reach like really high strength, right? And you can see that if we cure the concrete at 1 day and at 28 days, at room temperature, 25 degrees Celsius, the strength at 1 day is a lot lower than strength at 28 days. Okay. As you can see in this picture here, the strength at 28 days is about 40 megapascal. The strength at 1 day is about 10 megapascal. So that's 4 times the strength. Right? Right. So to reduce the cracks, we should maintain hydration by cover it and add some water. Right. So that's the curing process. You can see the strength after 7 days and after 28 days as well. Right. So there's quite a huge difference in strength after 7 days and 28 days. Right. So curing is important. We don't want the water inside of the concrete to evaporate out. We want to keep it in there for the hydration reaction to complete. Okay, so the reason for that is, as mentioned earlier, the strength of concrete comes mainly from B light, right? The ultimate strength, the final strength comes from B light. And B light reacts really, really slowly with water. It takes up to 28 days to get up to the maximum strength, or close to the maximum strength. Right? Sometimes it takes years to get to the maximum strength. Right? If we can keep the water inside the concrete, right? It will develop strength. It will develop strength or have increased strength years after it is first produced. Okay. Important factors that influence the properties of concrete. The first one is the water to cement ratio. Okay. If you have too little water, you will have low strength, right? Because you don't have enough water for the hydration reaction. Okay. If you have too little water, you don't have enough water for the hydration reaction to occur. So you get low strength. If you have a high water cement ratio, you will improve workability of the concrete. That means the concrete can flow much easier. You can shape it into the shape that you want much easier in a longer period of time. And workability can be measured by using a test called slump test. We'll look at some tests in a bit. But if we have too much water, right, we will have a decrease in compressive strength. And we will have an increase in shrinkage of concrete during curing and create cracking, right? So if we have too much water. So we need an optimum amount of water, not too low, not too much. An optimum amount. And another factor that can affect the properties of concrete are the amount of air entrainment. Okay, so basically, in concrete, you have pockets of air, bubbles, right? When the concrete is set and becomes solid, you have pockets of air or bubbles of air trapped in there. That is called air entrainment. Okay. The small amount of air entrainment is good, right? So we want about 1 to 2.5% of air entrainment in concrete to make it easier to pour. If you don't have any air at all, it will be more difficult for concrete to flow, right? So basically, we have a little bit of air by actual pouring of concrete itself, by adding an admixture to or adding an additive to include air entrainment. Okay, the entrained air improve the workability of concrete. So if you have pockets of air inside like soft concrete, that the concrete can flow much easier. So you have better workability, right? And if you have small pockets of air in hardened concrete, it will minimize the problem with shrinkage and free flow uh, condition, right? So in colder country, in winter, when you have snow and snow melts, and then at night it will freeze, right? The water from the melted snow become ice on the road, and in the morning it will melt again, and the water will seep through the cracks, and then at night it will freeze again. Like in this free fall cycle, you can make the road surface like damaged quite easily. By having some pockets of air or entrained air inside your concrete, you can accommodate the expansion by the expansion of water turning into ice without like cracking the concrete structure itself. Okay, so entrained air is good. Increase workability, increase freeze fall resistance. But if you have too much entrained air, you have lower strength, right? Because instead of having cement or aggregates in that place, you have air. So you don't have any mechanical property because you have air. But if you have cement or concrete there, it will be stronger, right? So if you have too much air, entrained air, you have too much empty space, you have lower strength. Quite sensible, really. Okay, and the next factor that influence the properties of concrete are the type and amount of aggregate. Angular aggregates are required, right? So, like I mentioned earlier, angular aggregates are preferred because of the mechanical interlocking between the aggregates themselves. Um, we want smaller aggregates, right? Smaller aggregates give you better strength, but smaller aggregates require more water as well because smaller aggregates have larger surface area to volume ratio, right? So water molecules can absorb on the surface much more, right? So you need more water. Um, the volume ratio of aggregate in the concrete is based on the bulk density of the aggregate, about 60% of the true density. Okay, so the aggregate itself is not like completely dense, completely solid. You have holes inside the aggregate. So the bulk density is roughly about 60% of the like um of the true density. Right? And the strength depends on the bulk density. Okay, so we were talking about workability of concrete, and a way that we can test for workability of concrete is by using a slump test, right? So we will look at a slump test. Okay, so when we mix a sample, when we mix a concrete to use in like casting a structure or doing anything, we take a sample of concrete, we put that sample of concrete inside a cone, this shape here, this cone shape equipment, about 30 centimeter high. On one side, it's got 10 centimeter diameter. On the other side, it's got 20 centimeter diameter, right? So you turn the cone upside down first. So the smaller side on the floor, right, initially. And then you pack in concrete. You pack in concrete inside the cone. And then you turn it right side up. So you put the larger end on the floor. Okay? And when you put the larger end on the floor, you take off this cone here. You get this concrete slump. Right? You get the concrete slump. And if you can see in this picture, you have the concrete slump next to the cone itself. Right? And then we measure the height of the top, the height at the top of this concrete slump and the top of the cone. Okay, so we measure the height difference between the top of the cone and the top of the slump, right? So we're measuring the height. Okay, so for concrete with zero slump, you can see that after you're taking the cone out, and when you measure the slump, that's zero slump. That means the top of the cone, the top of the slump is the same height as the top of the cone, right? Which is not very good because you don't have any slump at all. That means it is really difficult to flow. We want a true slump. We want a true slump where the concrete flow down a little bit, right? So you have a little amount, right? The slump test usually is reported in terms of centimeter, like how many centimeters different between the top of the slump and the top of the cone, right? So we want true slump, right? The concrete hold its shape, but not the same height. Okay, we don't want any collapse slump or shear slump. Okay, if we have collapse slump or shear slump, that means we do not have good quality concrete, let alone poor workability, right? So for zero slump, no workability at all. For collapse slumps or shear slump, we have really poor quality concrete. Okay, we want true slump. Like true slump will give you like good quality concrete and good workability. Okay, the factors that affect the workability of concrete. One of the factors that affect the workabilities and properties of concrete is air entrainment. Okay, so we can use surfactant to increase air entrainment. Mainly, we control the air entrainment to prevent against the freeze thaw damage by creating air bubbles or entrain air inside our concrete. And we put in like some air inside the concrete there. Okay, so a quick question, right? So we know about concrete, and sometimes if you consider the road surface, sometimes it's not concrete, right? We have asphalt mix, right? Sometimes we have asphalt mix on the road and not concrete. So the question is asphalt mix a composite material? And if it is a composite material, what is the matrix and what is the reinforcement? Okay, so is asphalt mix classified as composite material? If it is a composite material, is it MMC, PLC, or CMC? What is the matrix? What is the reinforcement? Right, so we have to consider the asphalt mix. Right, so asphalt is basically bitumen. Okay, bitumen is an organic binder. We get bitumen from distillation of crude oil. Okay, and so bitumen is an organic binder composed of hydrocarbon with low melting point. We get bitumen in from a product of distillation of crude oil. It's got low melting points, and it is a thermoplastic polymers. Okay, so basically, asphalt mix is a composite of aggregates and bitumen, right? So instead of using cement, we're using bitumen instead of cement in the asphalt mix, right? So the aggregates, in this case, should also be angular, just like in concrete, right? The aggregate should be clean, should be angular, just like in concrete. The aggregate should have distribution of grain size to provide a high packing factor and good mechanical interlock between aggregate grains. So, is asphalt mix a composite? Yes, it is. What type of composite is asphalt mix? It is a polymer matrix composite because the matrix is bitumen, and bitumen is an organic binder or thermoplastic, right? So it is a polymer matrix composite. And what is the reinforcement in asphalt mix? The reinforcement is the aggregates or the rocks used just like the rocks that are used, crushed rocks or gravels that are used in concrete structure. Okay, so we've learned about different type of particles reinforced composite. Next, we will look at the properties of the particle reinforced composite, right? So, as you might imagine, the properties of the particle reinforced composite should have the properties between that of the matrix and that of the reinforcement, right? So we will look at the different properties of particle reinforced composite, right? So we'll take a look at an example of elastic modulus of the composite, or EC, right? E is the elastic modulus, and C is for composite, right? So elastic modulus, EC, of composites, we can have two approach. So we can find the upper bound or the upper limits and lower bounds or the lower limits. And our material, we have mechanical properties between the upper bound and the lower bound. Okay, so for the first approach, we assume that the bonding between the matrix and the aggregate or reinforcement is perfect, right? So in that case, for the upper bound Young's modulus or elastic modulus, we have EM VM plus EP VP equals the elastic modulus, right? So when EM is the elastic modulus of the matrix, VM is the volume of the matrix or the volume fraction of the matrix, plus EP, which is the elastic modulus of the particles, and VP is the volume fraction of the particles in the composite. Right, so you can see that it is the mixed properties of the matrix and the reinforcement depending on the volume, right? So for example, if you have 100% matrix and you don't have any, if you have 100% matrix and you don't have any reinforcement at all, right? So 100% matrix, you have volume fraction of 1, volume fraction of 0 here. So this term becomes 0. So elastic modulus is just the elastic modulus of the matrix times 1. So it's elastic modulus of the matrix, right? So the upper bound approach assume the perfect bonding between the matrix and the reinforcement, and depends the value of the elastic modulus depends on the volume fraction of the matrix and the particles, right? So if you add more particles, you have more higher volume fraction of the particles, and the particles usually have high elastic modulus compared to the matrix, then you will get higher elastic modulus, right? So if you look at the elastic modulus, and if you look at the upper bound, you get this linear relationship between elastic modulus and volume fraction, right? So 0% constant, that means we have 0 volume fraction of the particles, yeah? So you get the modulus of the matrix only. Here you get modulus of the reinforcement only. So in between, it depends on the amount of the reinforcement, right? So that's the upper bound. For lower bound approach, we assume that the bonding is not perfect. You have some tearing of the bonding, etc. So we get this elastic modulus, lower bound, equals EM times EP divided by VMEP plus VPEM. Okay, so we get this curved line here. This is the lower bound limit. Right? So for example, if we look at 50% constant somewhere around here, right? So we know that in a perfect world, the upper bound, the modulus would be somewhere around here. In a not so perfect world, it can be any value, like along this line at 50%, like along this line here. Okay. So this approach can be applied to other properties as well, like electrical conductivity, sigma E, like electrical conductivity, replace E elastic modulus with sigma E. Thermal conductivity, replace E with K, etc. Okay, an example, a large particle composite consisting of tungsten particles within a copper matrix is to be prepared if the volume fraction of tungsten and the copper are 0.4 and 0.6 respectively. Estimate the upper limit and lower limit for the specific stiffness of this composite given the data that follows. Right? So specific gravities 8.9 for copper, 19.3 for tungsten. Modulus of elasticity is 110 gigapascal for copper and 407 for tungsten. Right? For upper bound approach, the elastic modulus is EMVM plus EPVP, right? So we just plug in the number. The matrix is copper. E copper is 110. Volume fraction is 0.6 plus E particle, which is tungsten, is 407. Volume fraction of 0.4, right? So calculate that, we get 228.8 gigapascal, right? Quite simple, really, for upper bound. For lower bound, we use the different formula, right? So we have EMEP over EMVP plus EPVM, right? We plug in the number, we get 155 gigapascal. So in other words, for this particular composite material, the elastic modulus is somewhere between 155, which is the lower limit, and 228 gigapascal, which is the upper limit. Okay, so we've talked about particle reinforced composite. Next, we'll look at the fiber reinforced composite. Right? So for fiber reinforced, we can have viscous, which is really short fiber, thin single crystal, right? Thin single crystals, large length to diameter ratio of graphite, silicon nitride, silicon carbide, high crystal perfection, extremely strong, very expensive, right? So when we are talking about viscous, we are talking about single crystals. That means that fiber, that whole fiber is one crystal, right? And because of that single crystal, it is very expensive to form, but it is extremely strong because it is a single crystal with high crystal perfection, so there's no defect. So that makes it really, really, really strong. Right? For example, silicon carbide viscous or boron nitride viscous. Okay? For fibers, we can either have polycrystalline or amorphous. Notice the difference here, right? Viscous, you have single crystal. For fibers, it can be polycrystalline or amorphous. Okay, that's the difference. The size can be about the same size, right? For fibers, generally polymers or ceramics. For example, aluminum, Al2O3, aramid fiber, glass fiber, boron nitride fiber, ultra high molecular weight polyethylene, UHMWPE. Right? So these are example of fibers, right? Polyaramid fiber, fabric of woven carbon fiber, and this is fabric of woven carbon and Kevlar fiber. Okay, so you can notice the picture here, right? So when you have just the carbon fiber, you have like black fibers, black gray fibers, depending on how it catches light, and aramid fiber. Our polyaramid fiber is the general name, right, of a type of fiber, which we usually know by its commercial name or a trademark name of Kevlar, right? So if you buy Kevlar and it doesn't come in yellow fiber, you're buying fake Kevlar, right? Because Kevlar is produced by DuPont. Kevlar is produced by DuPont, and it is a trademark of DuPont, and DuPont produced Kevlar in yellow only, right? But you can have other manufacturers that can produce polyaramid fiber in other color, like black color as well, right? So it doesn't mean you have like fake polyaramid. It just means that you have fake Kevlar, right? So because of the two type of fibers, carbon fibers and Kevlar fibers have different colors. So when you like weave them together, you get this like distinctive pattern. Okay, and Kevlar fibers are about 5 times stronger than steel in tension, like steel all the same size in tension. Okay, so next we have possible arrangement of fibers in fiber reinforced composite material, right? So many different ways the fibers can be rearranged, right? So when we have short fibers or discontinuous fibers, we can have discontinuous and randomly oriented fibers. So the fiber's direction doesn't matter. It's just random, right? The fiber is just pointing everywhere, okay? Or we can have short fibers or discontinuous fibers, and the fibers are aligned, okay? So these two pictures, you can probably guess that even though they are made from the same matrix, even though they are made from the same reinforcement, same volume fraction, everything, the properties would be different, right? The properties of these two material would be different because of the different arrangement of fibers. Okay. Okay. When you have long or continuous fiber, you usually have aligned fibers, right? Because continuous fibers can be easily aligned or can be woven into fabric, just like in this case here, right? So when the fibers are woven into fabric, basically you can have fibers that are aligned in two directions. Right? So you have fibers that are aligned in this direction and in this direction. Okay. And when I mentioned that these two pictures, even though if they are made from the same materials, the same matrix, the same reinforcement, and the same volume fraction, they will have different properties. Right? But why is that? Because the uh, the fibers are strongest in the direction of the loading, the stress, right? So if you look at this aligned continuous fiber, aligned discontinuous fiber, and randomly aligned fiber, you can see that for aligned continuous fiber, it is very strong in this direction, or the direction of the fiber, and it is very weak in the transverse direction. Okay, because the fibers do not help transferring the load at all. Right, so it is very weak in this direction. It is very strong in this direction. Okay, and when you have different properties in two directions, like in this case here, we call that material an anisotropic material, right? Somewhere at the bottom of the slide there. Anisotropic material, which means the properties of the material depend on the direction. Okay. The same thing with shorts or discontinuous fiber that are aligned. You have better property in the direction of the fiber compared to the transverse or any other direction. Okay. So they are anisotropic as well. Okay. For aligned discontinuous fiber. Aligned discontinuous fiber. Anisotropic means the properties depends on the direction. Okay. But when you have randomly aligned fibers, when you have randomly aligned fibers, you don't have any preferred direction, right? So if you load it in this direction, or if you load it in this direction, it would be the same because fibers are random in all directions. Okay, so in this case, this material is called isotropic, which means it has the same properties in all directions. Iso is the Greek roots for words like that means the same, right? Like isomer, um, isotherm, isomer, etc. Iso means the same, right? Isotropic means has the same property in all direction. And to make isotropic negative, we add an, right? That becomes anisotropic. Right? So from isotropic, which means the same in all direction, we add prefix an. It becomes anisotropic, which means not the same in all direction, right? Which is the properties of aligned fibers, composite material. Okay. Examples of fiber reinforced composite, right? So we find this a lot nowadays in cars, right? We used to find it in like expensive cars, sports car, supercars, etc. Nowadays, we find this a lot in even like commercial vehicles, like normal cars, right? Like bumpers in normal cars nowadays, we have glass fiber reinforcement in there to increase the strength as well. There are other parts like the monocoque, the body panel, etc. Right, so there's a lot of carbon fiber reinforced polymer used in the car. Okay, an example of fiber reinforced composite aligned continuous fiber is well, we have a look at two examples. The first one is silicon carbide copper as a material for heat sink for fusion reactor. Right, so um, basically you have a heat load from the fusion from the nuclear fusion, right? And we have a plasma facing material. So we have a coating so that these material here doesn't sort of like disintegrate it when you have like such high load of from heat and plasma. And in the heat sink we have copper reinforced with fibers of silicon carbide. Okay, so in the heat sink here, in this picture, this is a true micrograph of this application here, right? So we have copper, and the black dot there is the silicon carbide fiber. The copper is the matrix, and silicon carbide fiber is the reinforcement. Okay, so we choose copper for this application because copper has very high thermal conductivity. So we want to transfer the heat um, from the nuclear reaction to the heat sink and transfer the heat to to dissipate the heat basically, right? So we want copper because to transfer the heat because it's got high thermal conductivity, so it can transfer heat really really fast. But at high temperature, copper becomes softer. At high temperature, copper becomes softer. So, or in other words, it loses its mechanical properties. So we want to increase the mechanical property of copper at high temperature. So we reinforce it with silicon carbide fiber, right? So it's got high mechanical properties at elevated temperature. Okay, so we improve the properties of the matrix, especially high temperature property of the matrix, while using the good characteristic of the matrix, which is the high thermal conductivity. Okay, so this is an example of this material. And if you look more closely, you can see like some sort of boundaries between like in the copper matrix as well. Because the way they produce this, they are coating silicon carbide fibers with copper, and then they are stacking those copper coated silicon carbide fibers together, and then they press them together, and then they heat them to make like a big chunk, right? So they start off with like silicon carbide fiber and start coating that fiber with copper, and you do that to a lot of silicon carbide fiber, and then you stack them together, and then you heat them up, you get this bulk of silicon carbide reinforced copper heatsink. Next is the glass silicon carbide fiber. Okay. In this case, glass as the matrix, right? Glass has really low um, elastic modulus compared to silicon carbide, right? So we add silicon carbide in there to increase the um, to increase the stiffness or elastic modulus of glass, and also to improve the toughness or K1C of glass as well. So the fracture surface becomes more ragged instead of like flat uh, fra- uh, fracture surface of glass, right? So that means it can absorb more energy. Okay. Another example of discontinuous fiber. Okay. So for discontinuous fiber, you can have discontinuous fiber randomly arranged in 2Ds or randomly arranged in 3Ds or like 1D, right? Okay. So for discontinuous fiber, okay. So it is this in this example, it is discontinuous. That means it's got short fiber reinforcement, random 2D fibers. That means it is random. Um, it is random in two directions, right? So in this direction and this direction, but it is like sort of aligned in this direction, right? So one of the three axes, the fibers are aligned, and the other two axes, the fibers are sort of randomly oriented. Okay? The carbon fibers are very stiff, very strong, and we have the carbon matrix, which is less stiff, less strong than the carbon fiber. So we can see that the carbon fiber lie flat in a plane. Right? So if you take a cross section, you see that the carbon fiber lie flat in the plane. But on the plane, you can see that they are sort of randomly arranged. So to make this, you tip the carbon fiber inside of a pitch, which is like some sort of tar, hydrocarbon, really thick hydrocarbon type thing. Right? You tip it in there, and then you burn it off. Right? You tip it in there, and what you compact into the shape you want, and then you burn off the hydrocarbon. Right? So you are left with the carbon matrix that is bonding to the carbon fiber, right, at 2,500 degrees Celsius. We use this in disc brake gas turbine exhaust flaps and nose cone. Right, nose cone in rockets, gas turbine exhaust flaps in jet engine, disc brake in a brake pad, right? So when we're talking about disc brake consists of two parts, right? You have the disc that is sits sit on the axle of the car, right? And you can see the disc, like metal disc. Usually, well, they are made of metal usually, but you can have high performance ceramic disc as well. And you have the brake pad, in this, which is in this application here, right? You have the brake pads that is made from carbon fiber composite. Okay, so the carbon fiber is really hard, really strong, so it can grip on the brake disc quite firmly and stop the car quite quickly. Okay, okay so um, the enhancement of composite properties by variation of fiber length. So for fiber reinforced composite, right? We have continuous fiber and discontinuous fiber, and the fact that we have discontinuous fiber means that different different size of fibers can affect the reinforcement differently, and we need um, a, a minimum size that we can classify that type of uh, composite as fiber or short fiber compared to particles, right? So if the size of the fiber is smaller than this minimum size, it can be considered particle. If it's more than that, it can be considered short fiber. And if it's longer than the maximum short fiber length, it can be considered long fiber or continuous fiber. Okay, so the minimum length that we can consider it a short fiber is called the critical fiber length, or LC, right? Which LC equals sigma f times d divided by 2 tau c. When sigma f is the strength in tension of the dispersed phase, or the strength of the fiber, right? F for fiber. So sigma f is the strength of the fiber. D is the diameter of the fiber, and tau c is the shear strength at the fiber and matrix interface, right? So the shear strength between the reinforcement and the matrix. Okay. So if you put in the value for your fiber and you get the value for LC, right? You put in the strength of the fiber, you put in the diameter of the fiber, and the shear strength of the fiber matrix interface, you get the value of the LC. If the length of the fiber that you use is shorter than LC, it is not a fiber, it is a particle, right? But if it is longer than LC, that means it can be effectively reinforcing your composite as a fiber, okay? And if it is longer than LC but less than 15 LC, we can call that a short fiber, right? For a short fiber, discontinuous or short fiber is when you have the fiber length of less than 15% I'm sorry, 15 times critical length, or LC. Okay, so this is a discontinuous or short fiber. But if the fiber length is longer than 15 LC, this is called a continuous, right? So we have this criteria for continuous fiber, discontinuous short fiber, and like particle. Okay, so if the length of the fiber is shorter than the critical length, it is not effective as a fiber. In that case, it is then reclassified as a particle. Okay, and if the length of the fiber is less than 15 LC, it is called a short fiber reinforcement because it has poorer fiber efficiency. You can see that the fiber intercept like lesser amount of the stress line, right? So, okay. But when you have longer fiber, you have better fiber efficiency. Okay, so for particle reinforced composite, we were looking at properties of particle reinforced composite, and we use upper bound approach and lower bound approach to estimate the strength or stiffness or other properties of particle reinforced composite, right? For continuous fiber, for fiber reinforcement, we can use the same approach as well, right? So the estimate of elastic modulus of the composite and tensile strength of the composite, in this case, it is valid for continuous fiber composite, right? So continuous fiber composite means long fiber, continuous fiber, and the elastic modulus is EC, elastic modulus of the composite, equals EMVM plus KEF, VF. When EM is the elastic modulus of the matrix, VM is the volume fraction of the matrix, EF is the elastic modulus of the fiber, VF is the volume fraction of the fiber, and K is the efficiency factor. And the efficiency factor depending on the alignment, whether it is 1D aligned, 2D aligned, or 3D aligned. Okay, so usually if you are asked to calculate the properties, all these values will be given, but you have to pick and choose the correct value to put in the formula. Okay, tensile strength in fiber direction. Okay, tensile strength in fiber direction is tensile strength of the matrix multiplied by the volume fraction of the matrix plus tensile strength of the fiber times volume fraction of the fibers if it is aligned 1D, right? Because if it is aligned 1D, the K factor, the efficiency factor is 1, right? When it anisotropic. So the K value is 1. But if it's random 2D, the K value is like 3/8. If it's random 3D, then it's 1/5, etc. Right? So you have to choose the efficiency factor accordingly, depending on the alignment. Okay, an example: a continuous and aligned glass fiber reinforced composite consists of 40% by volume of glass fibers having a modulus of elasticity of 69 gigapascal and 60 volume percent of a polyester resin that when hardened displays a modulus of 3.4 gigapascal. Compute the modulus of elasticity of this composite in the longitudinal direction. So the keyword in this example is the longitudinal direction because it gives you a hint that it is aligned, right? It is aligned in 1D, and you have to calculate it in the longitudinal, which is the direction of the fiber, right? Okay, so having said that, you have to pick this formula here, right? And because of the keyword of longitudinal direction, we know that it's aligned 1D, so we put in the K value of 1, right? Okay, so elastic modulus of the matrix is the resin, right? The resin has the elastic modulus of 3.4 gigapascal. The volume fraction of the resin is 60%, which is 0.6, plus efficiency factor 1 times the elastic modulus of the fiber, which is 69 gigapascal, times the volume fraction of the fiber, which is 40%, which is 0.4. That gives you 30 gigapascal. All right, easy peasy. Next, we will look at the structural composite, right? Structural composite, like I mentioned in the start of the class, that is a little bit different than particle reinforced or fiber reinforced, right? It's different because for particle reinforced or fiber reinforced, you mix in the reinforcing phase inside the matrix. But for the structural composite, the reinforcement and the composite, the reinforcement and the matrix are sort of like sitting on top of each other, like in either a laminate or sandwich structure. A laminate is stacked and bonded fiber reinforcement sheets with stacking sequence of, say, for example, 090 or 04590, depending on the application. The benefit of laminate is balance in plane stiffness, right? So basically, you have fibers running in one direction, right? And you stack it on another layer with fiber running on another direction, depending on the stacking sequence, right? So if you call this 0 degrees, the next layer will be 90 degrees, right? And then go back to 0, and then go back to 90, okay? Like I mentioned earlier, you can have 0, 0, 45, 90, 0, 0, 90, etc., right? Depending on the application. So in this case, it's 0, 0, 90. So you have good property in this direction, the direction of the fiber in this layer, right? But also you get good property in this direction. So that's a property, that's the fiber direction in the second layer, right? And you have alternate layers of the two directions. So you get good properties in all like 4 directions, okay? So that you get balanced in plane stiffness. Okay, you get the same property whether it is bending this way or this way, right? Whether this way or this way. Okay, this is called laminate. It is called laminate because you have sheets of fibers, right? So fibers stacked together in a sheet, and then you stack those sheets together. Okay, laminate comes from Latin roots of lamina, which means sheets. Okay, and then you stack them together. Okay, next is the sandwich panel. Just as the name suggests, sandwich panels means you have 2 panels acting as the bread of the sandwich, and then you have something inside, right? So in this case, an example, in this case, you have aluminum face sheets, and then you have adhesive, right, to stick the honeycomb inside, right? Honeycomb structure is sort of the hexagonal beehive structure. So you make your polymers or your papers or sometimes even like aluminum foil into this honeycomb structure, and you stick the honeycomb structure between two face sheets, right? And the face sheet can be quite thin as well to lower the density, right? So the sandwich panel gives you low density of the face sheet and the honeycomb core, but it will give you really good bending stiffness. It doesn't bend easily. So, like I mentioned earlier, the floor on the airplane that you walk on are usually this type of sandwich panel, right? It doesn't bend when you walk on. It feels really stiff. It feels really solid, right? But it is really lightweight. Okay, this is a type of sandwich panel, and in 787 Dreamliner, you can see that there's a lot of composite material, and a lot of it are carbon laminate composite, and also carbon sandwich composite, right? So there's a lot of composite material, especially laminate and sandwich panel, right? About 50% by weight of the plane is made from composite material. So it's quite scary, really, when you think about it, that 50% by weight of the plane is made from plastic, mainly. Right? But, well, having said that, it is composite material, so the strength is better than like pure plastic, and also it's coupled with other type of materials as well. Another type of structural composite, another example, another type. Okay, this is a combined laminate and sandwich structure. So you have laminate of carbon fibers as a face sheet, and you have honeycomb, aluminum honeycomb structure in between, right? So you have the sandwich of the laminates, right? You have laminate face sheets, and you have aluminum honeycomb inside. So you get the laminates and sandwich together. So you get really, really good mechanical properties and really, really light. And it is used in Formula One cars, like supercars, hypercars. Another example is of structural composite are skis, right? So for skis, you have different layers, and each different layers perform different functions, right? So you get the top layer, usually made from wood or polymers, right, to maintain stiffness. You get fiberglass to increase the triaxial stiffness, etc. Right? You have hardened steel edge to dig in the hardened snow, right, so that you can turn quite easily, etc. So skis are example of structural composite. Um, okay, summary. Composite are classified according to the matrix, like CMC, MMC, PMC, right? Ceramic matrix composite, metal matrix composite, and polymer matrix composite. Reinforcement geometry, right? The composite are classified according to reinforcement geometry, like particles, fibers, layers, laminate, etc. Composite composites enhance metric properties. In MNC, you increase the yield strength, tensile strength, increase performance. For CMC, the metric is ceramic is quite brittle, so you want to improve the fracture toughness, right? For PMC, the metric is polymer, which is quite weak, not very strong, so we want to increase the strength and stiffness, right? Elastic modulus, Young's modulus, tensile strength, and free performance. Um, for particulate reinforced, uh, the elastic modulus can be estimated using the upper bound approach and lower bound approach. The properties of particle reinforced composite are isotropic. For fiber reinforced composite, the elastic modulus and tensile strength can be estimated along the fiber direction. Properties can be isotropic or anisotropic. The properties are isotropic when you have random arrangement of fibers, and the properties are anisotropic when you have aligned fibers. For structural composite, the structural composite is based on build-up of sandwiches in layered form. Okay, I'm going to give you a quick overview of composite in dentistry, right? So usually when you have filling, well, when you have tooth decay and you want to fill it, right? Uh, they used to fill it with gold, right? And then amalgam, right? Because amalgam is cheaper than gold. That's the main reason. Nowadays, you can have composite material, right? The composite is called dental composite, and usually consists of resin and particles of glass or some sort of minerals. Like so, it is basically a particle reinforced composite, and it is also a polymer matrix composite, right? Because you have a resin which is a polymer and reinforce it with particles of glass or ceramics or alumina, etc. Right? And the way you apply it is by using this like squeeze needles. So basically inside this tube here you have the resin and the particles mixed together already, and then you squeeze it in there and you shape it into the shape that you want, and then you leave it to cure. It can be natural cure or usually it is UV cure, right? So basically you have to shine UV light on the teeth, similar to when you have a nail extension, right? They put on the glue, the UV glue, put on the nail extension, put it under the UV light to kill the glue, right? The same stuff. Okay, and you can see that it can has well, it can have like quite good appearance. It's very similar to real tooth, right? In appearance compared to amalgam or gold, right? Which is like quite distinct. Okay, and nowadays the performance is reasonable. It is close to the performance of amalgam without like looking different. Like it will look like you don't have any feelings. You have like beautiful, healthy teeth, when in fact you don't. But anyway, so this is just like one type of composite material that is used in dentistry. Another type is uh, another example that I want to tell you about is the use of 3D printing in dentistry, and specifically 3D printing composite material. Right, so you have 3D printed composite material bridge and 3D printed composite material uh, crown, right? So basically, you can do 3D scanning of a patient jaw and teeth, right? You can do X-ray, CT scan, MRI, or whatever, and you get a 3D model of the patient jaw and teeth, and then you can manipulate that on the computer to to get the denture of that to get a new denture for that patient, right? So you can print out the whole set of denture or a whole set of like customized dental product. You print it out using 3D printing. Okay, so that's